Well, today let us discuss about applications of Syringer equation. Okay, by application means we will think of some system. Okay, then we will write the Syringer equation for the system, and then we will solve it. Okay. So we'll consider a system, number one. Number two, we write the Syringer equation for the system. And number three, we solve the Syringer equation for the system. Okay, so that is all about applications of Syringer equation. Okay, so let us consider a system which we generally call as particle in one dimensional box. Okay, we generally call it particle in one dimensional box. So this is the system we have considered. Now, what is there in this system? What is there in this system? We consider one particle of mass m moving in x dimension. Okay, so we consider one particle of mass m moving in x dimension, one dimension. Okay, one dimension, that is x dimension. Okay, mass of the particle is m, and we further consider that let the particle be confined between two potential walls, one at x equal to 0, the other at x equal to, say, a. Okay, so as if these are the two walls. One wall is at x equal to 0. The other wall is at x equal to a. So the length of the box is a. Now these two are potential walls. What does it mean? It means that outside this wall, potential energy is very high. From this, potential energy is very high, but here potential energy is 0. Therefore, so potential. Okay, so we are in the potential field of the earth. That means we are in the gravitational attraction from the earth. Okay, I repeat, say we are in the potential field of the earth. What does it mean? That means we are attracted by the earth. Okay, gravitational attraction is there. So that is potential. Okay, so outside these two walls, very high potential, infinity, and within these two walls, potential is 0. There is no attraction or repulsion. You may think like this. Outside this, huge attraction or repulsion, but here no attraction or repulsion. You may think like this. So these are the two potential walls. Okay. So here what happens? Here what happens? V potential is 0 within the limit 0 x a, within the limit this, and V is infinity when x is, x is less than 0 and x is greater than a. Okay, potential is infinity. Okay, so you may say less than equal to 0, less than greater than equal to a. Okay, this is the condition. Now this is our system. We have considered this system. So application of Schrodinger equation means we have to consider a system. So we have considered the system. Okay. Then we will write the Schrodinger equation. So a particle is moving in x dimension. What is the Schrodinger equation? Schrodinger equation time independent. Time independent Schrodinger equation. Time independent Schrodinger equation, okay, for the particle is minus h bar square by 2m d2 psi dx square plus v psi equal to e psi. So this is the time independent Schrodinger equation for the particle. Okay, mass of the particle is m, it is moving. So this is the time independent Schrodinger equation, and we are not writing partial differentiation because we are considering only one dimension. Okay, that means one variable x. Now here particle is here, so we are considering this system. Particle is here. Okay, we are considering this system. So here v equal to 0. Since v equal to 0, so from 1 what we get? Minus h bar square by 2m d2 psi by dx square equal to e psi. Okay, e psi. Or we can write it like this. If we divide both sides by this, dividing both sides by this, what we get? d2 psi by dx square plus 2me by h bar square equal to 0. Okay, psi equal to 0. Now here m, mass of the particle, is constant. E, total energy, that is constant. H bar means h by 2 pi, constant. So whole this thing is constant. 2me by h bar square. Whole this thing is constant. Let us write this. Say k square. K square equal to 2me by h bar square. Let us put this. In that case, equation will be d2 psi by dx square plus k square psi equal to 0. So now the equation is this. Okay. Now this is second order differential equation, and we discussed how to solve this type of differential equation. We discussed about that. Okay, I repeat, this is second order differential equation, just like d2y by dx square plus k square y equal to 0. Okay, and we have already discussed how to solve this type of differential equation. And to solve a differential equation means we have to find out the value of psi. Okay? So you definitely remember what the general solution to this equation is. Okay? So the general solution to 2. What is the general solution? Psi equal to a cos kx plus b sin kx. So this is the general solution. We have already discussed about this, so I am not going to repeat. Okay. So this is the general solution to this equation. That means if we solve this equation, we will get the value of psi as this. Okay. Now we have already said that depending on the value of theta, that is x, we will get so many values of psi. Okay. Depending on the value of x, we may get thousands of values of psi. But all those values of psi may not be significant. So we have to find out those values of psi which are significant. Okay. Now, how to find out the significant values of psi? How to find out the meaningful values of psi? For that, we impose 3 conditions. Okay. Psi must be single valued, psi must be continuous, and psi must be finite. Okay. Now we know sine function, cos function, both are single valued. Okay. We know sine function, cos function, both are continuous. Okay. And we further know that sine, cos, both are finite, because maximum value plus maximum value plus 1 or minus 1, minimum value is also plus 1 or minus 1. So if we consider that psi must be well behaved, that is single valued, continuous, finite, so all conditions apply here. But problem is that psi must be single valued, psi must be continuous, psi must be finite with respect to our system. Okay. মই আকৌ এবাৰ কৈছোঁ, আমি যদি এনে চাওঁ সাইন ফাংশন, কস ফাংশন, both are single valued, continuous, finite, no problem. But here a condition is that psi must be well behaved with respect to our system. That means psi must be single valued, psi must be continuous, psi must be finite with respect to this system. Now let us see that. Say psi must be continuous. Psi must be continuous means from that condition. Psi must be continuous from that condition. What result we may obtain. Okay. Psi must be continuous from that condition. What result we obtain here. Okay. So you see, if we plot psi in this region, okay, in this region, x is less than 0. In this region, if we draw graph between psi, in this way psi, and in this way x. If we draw graph between psi and x, what should be the nature of the graph? Now here you see, we consider that the particle is here. We consider that the particle is here. So the probability of finding the particle cannot be 0 here. So psi is not 0 here. Psi is not 0 here. But outside, potential is infinity. That means probability of finding the particle is very, very less, almost 0. Almost 0. Psi square is 0. That means psi is 0. So outside this region, psi is 0. Outside this region, psi is 0. Because probability of finding the particle is almost nil, 0. Because particle is here, that means psi is 0. So if we plot a graph in this region, what will be the graph? Graph will be this only. Because whatever the value of x may be, psi is 0. Similarly, here also psi is 0. Here also psi is 0. So if we draw a graph between psi and x, the graph will be this only. Because whatever the value of x may be, psi will be 0 only. So this is the graph. Now at these 2 points, what should be value of psi? Okay, at these 2 points, x equal to 0, x equal to a. At these 2 points, what should be the value of psi? We have the condition that psi must be continuous. So here psi may have some value like this. But in order to be continuous, at this point, psi must be 0. Only then it will be continuous. Only then it will be continuous. So at these 2 points, psi must be 0 for psi to be continuous. Okay? That means at x equal to 0, psi equal to 0. At x equal to a, psi is 0. Okay? So these are the 2 conditions we get. These are the 2 conditions we get from continuity condition. Psi must be continuous. From that condition, we get these 2 results. And these are called the boundary conditions. These are called the boundary conditions. And they come from continuity condition. Okay, boundary condition. So if we apply that condition, say at x equal to 0, psi is 0. If we apply this condition in 3, what we get? If we apply this condition in 3, what we get? Psi is 0, a cos 0 plus b sin 0, x equal to 0, cos 0 1, sin 0 0, so that we get a equal to 0. Okay, because cos 0 1, sin 0 0. So from this condition we get that a equal to 0. So from 3 what we get? Psi is b sin kx, b sin kx. So this is the value. So you see, general solution is this, but if we apply the condition that psi must be continuous, that is well behaved, then psi must be this, not this. So for this system psi is this, not this. Okay, because boundary condition gives that a equal to 0. I repeat, for this system psi is not this, but psi is this. Okay, Now if we apply again this condition, x equal to a, psi equal to 0, if we again apply, where to apply? 4, because we no longer need this. Okay, so 4, from 4 what we get? Psi 0 b sine ke, b sine ke, or sine ke equal to 0. Okay, because b is constant, so we can write like this. Now sine theta equal to 0. Okay, sine theta equal to 0. So when sine theta becomes equal to 0? When n pi. Where n equal to 0, 1, 2, 3, etc. Because you see, n is 0, sine 0, 0. N is 1, sine pi, 0. N is 2, sine 2 pi, 0. So on. Hence Ka must be equal to n pi, or k square must be equal to n square pi square by a square. Okay, so this is a k n pi, this is 5. Now what is k square? K square equal to 2me by h bar square, k square, that is equal to n square pi square by a square. Now we know h bar equal to h by 2 pi, so here we can replace. So h bar square equal to this square, so we can replace this. Okay, and if we replace this and simplify, we will get that E becomes equal to n square h square by 8m a square. This simplification you can do. No problem. Very simple. Just substitute and simplify, you will get this result. This 6. Okay, 6. Now we have seen that k equal to n pi by a. So if we put here k equal to n pi by a. So if we put this, then from 4 what we get? Psi equal to b sine n pi x by a. So this is 7. Okay, so we have seen that value of n may be 0, 1, 2, 3, etc. We have already seen. Okay, and why n can have only these values? Because mathematically these are the possible values. Mathematically these are the possible values. Okay, and we have proved. There is proof that n can have values like this only. That means n can be 0 also. But here you see, if n is 0, then it will be sine 0. Sine 0 means it will be 0, which is impossible because here psi is not 0. Okay, if n is 1, 2, 3, etc., there is no problem. If n is 1, 2, 3, there is no problem. But if n is 0, there is problem. No? So here if n is 0, then psi becomes 0, which is impossible. So n cannot be 0. That is, n can be 1, 2, 3, etc., but it cannot be 0. Okay, so this is very, very important. This is very, very important. So we have obtained a quantity n, and first we observed that n may have values like this 0, 1, 2, 3, etc. But now we have proved that n cannot be 0. N can have only values like this 1, 2, 3, etc. Okay, n is called the quantum number. N is called the quantum number. Okay, quantum number. Now you see, so here in this energy expression, n is 1, 2, 3, etc. But it is not 0. N is not 0. N is not. Okay. Now from 4, okay, from 4 psi equal to b sin n pi x by a. We have seen that. Now we have to find out the value of b. We have to find out the value of b. B is a constant, and we have to find out the value of b. So how to find out the value of b? Okay, value of b. How to find out the value of b? By normalizing the function. By normalizing the function psi. That is equation 7. That is equation 7. We have to normalize. Okay. Now what is normalization? Normalization means integration psi square dx equal to 1. Probability. This is probability. And what is the limit here? What is the limit of x here? Limit of x is from 0 to a. So here normalization condition is this, because the maximum possible values of x are 0 to a. 0 to a for the system. So we know normalization means integration psi square dx must be equal to 1. And what does this mean? This means total probability within the range. Total probability within this range. Total probability. And total probability maximum, because maximum value of probability is 1. So this is normalization condition. So we put the value of psi here. What is the value of psi? B. B is constant, so I can take it out. 0 to a sine square n pi x dx. N pi x by a, dx equal to 1. Okay, n pi x dx equal to 1. So or we can write it like this: b square by 2 0 to a 2 sine square n pi x by a dx equal to 1. Okay, so we have already discussed about this. Okay, cos 2a, we have already discussed about this. Cos 2a equal to cos square a minus sine square a. Okay, that is equal to 1 minus sine square a minus sine square a. So 1 minus 2 sine square a. 2 sine square a. Okay, 2 sine square a. So 2 sine square a 2 sine square a equal to 1 minus cos 2a. 1 minus cos 2a. So 2 sine square a, 2 sine square a. For this I can write this. Okay, or b square by 2 0 to a 1 minus cos 2a 2 n pi x by a dx equal to 1. 2 n pi x dx equal to 1, or b square by 2 integration 0 to a dx minus integration 0 to a cos 2 n pi x by a dx equal to 1. Okay, so this is a, this portion is a, and this portion, let me show you. I can do it like this. Let 2 n pi x by a be equal to y. Okay, y. So 2 n pi by a dx equal to dy, or dx equal to a by 2 n pi dy. Okay, so this integration we may write it as cos y dy a by 2 n pi limit when x is 0 y is 0, when x is a y equal to 2 n pi. Okay, so integration this equal to a by 2 n pi, this is cos y, sorry, this is sine, integration sine, this is sine y 0 to n pi. Okay, 2 n pi. Now you see sine 2 n pi equal to 0 minus sine 0, so this portion is 0, so we can write b square by 2 a equal to 1. This portion is 0. Okay, so hence b equal to 2 by a whole to the power half. We generally take the positive value. Okay, hence we have got the value of b. So how we have got the value of b? By normalizing psi. How we have got the value of b? By normalizing psi. Okay, so this is known as normalization constant. Hence from 7, what is the value of psi? 2 by a whole to the power half. So psi equal to sine n pi x by a. So this is the value of psi. This is the number 8. So you see, by solving the Syringer equation for the particle in one-dimensional box, we have got two things. One is energy. Okay, one is energy, the other is wave function. Okay, I repeat, by solving the Syringer equation for particle in one-dimensional box, we have got two things. One is energy, the other is the wave function. So these are the two things we have got. Okay, now what is the significance of the energy expression? Okay, significance of the energy expression. Significance of the energy expression. Okay, number one is that here energy means it is total energy. What is total energy? Kinetic energy plus potential energy. Okay, E is the total energy. What is total energy? Kinetic energy plus potential energy. But here potential energy is zero. We have already said potential energy is zero. So here total energy means kinetic energy. So here total energy means kinetic energy, because potential energy is zero. Okay, kinetic energy. So this is number one significance. Here total energy means kinetic energy, since potential energy is zero. Now in classical physics, kinetic energy equal to half mvx square. Kinetic energy equal to this. Okay. Now where Vx is the velocity, and it may have any value from minus infinity to plus infinity. V may have any value from minus infinity to plus infinity, because velocity is a vector quantity, it has direction. Okay, so velocity may have any value. That means V may have any value. Since V may have any value, so kinetic energy may have any value. So kinetic energy may have any value. Okay. Vx may have any value within this limit, so kinetic energy may have any value. Okay. Any value of kinetic energy is possible in classical physics. But in quantum mechanics, what we get? Kinetic energy, that is kinetic energy equal to n square h square by 8m a square, where n equal to 1, 2, 3, etc. Now if n equal to 1, what is the kinetic energy? Kinetic energy equal to h square by 8m a square. Let me call it C. Now if n equal to 2, what is the kinetic energy? 4 h square by 8m a square. 4. Okay, 4 h square by 8m a square. We can write it as 4c. If n equal to 3, this is equal to 9c, and so on. So you see, any value of kinetic energy, that is total energy, is not possible. Only some definite values are possible. I repeat, arbitrary values of kinetic energy are not possible. Only some definite values are possible. That means in quantum mechanics, energy, that is kinetic energy, is quantized. Okay, kinetic energy is quantized. What does this mean? This means that arbitrary values not possible, only some definite values are possible. I repeat, in classical physics, any value of kinetic energy is possible. But in quantum mechanics, any value is not possible. Arbitrary values are not possible. Only some definite values are possible. That is, kinetic energy is quantized. Okay. So kinetic energy is quantized. This is the second significance. Now, since kinetic energy is quantized, so there will be some levels, energy levels. This is the lowest energy level, C, energy equal to C, lowest energy level. Next, this is the next energy level, E2, E2 equal to 4C. Next level. Next, another level, so E3, E3 equals to 9C. Then say E4, E4, E4 equal to say 16C, 16C. That means the particle may have kinetic energy this or this or this or this, but in between energy, that is not possible. The particle cannot have kinetic energy 2C, 3C, 1.5C, 1.1C, or the particle cannot have kinetic energy 5C, 6C, 7C, 8C. The particle can have kinetic energy this, not in between. So there are some energy levels. This is one energy level, this is one energy level. Okay, so there will be energy level. There will be energy level. Okay, these are the energy levels. You see. Now classically, if you look at the classical picture is like this. Say energy is increasing. Classically. This is the classical picture. And this is quantum mechanical picture. So one straight line means so many points. And each point will represent one energy value. So classically, all these energy values are possible. All these energy values are possible. But quantum mechanically, all these energy values are not possible. Only some definite energies are possible. That is quantized. So there will be energy level. Now you see, number 4 is that the spacing between two consecutive energy levels. Spacing between two consecutive energy levels. Increases as kinetic energy increases. Spacing. What is the difference here? 3C. What is the difference here? 5C. What is the difference here? 7C, and so on. So as kinetic energy increases, the spacing between two consecutive energy levels increases. Okay? Increases. So next thing is that So classically, velocity may have any value within this region. That means velocity may have value 0 also. Classically, velocity may be 0 also. So classically, kinetic energy may be 0. Okay? So classically, this is number 5. Number 5. Classically, Vx may be 0. So kinetic energy may be 0. May be 0. I should not write it. May be 0. May be 0. So kinetic energy may be 0. But quantum mechanically, kinetic energy cannot be 0. Cannot be 0. Lowest kinetic energy. Lowest kinetic energy is equal to h square by 8m a square. Lowest kinetic energy is this. So kinetic energy cannot be 0 since n cannot be 0. No? Since n is not 0. So kinetic energy cannot be 0. Okay, lowest value is this. So so lowest kinetic energy is this. Now you see momentum of the particle. Classically momentum of the particle equal to px square. Okay, I can write it as 1 by 1 by m into m square, p square. Okay, let me write it like this. Classically, kinetic energy equal to half m v x square. This is equal to 1 by 2m into m square vx square, that is equal to 1 by 2m px square. Kinetic energy equal to this. Okay. Now if you look at the lowest kinetic energy, so I can write that 1 by 2m px square equal to h square by 8m a square. So from this px square equal to h square by 4a square. So px equal to plus minus h by 2a. Okay, plus minus h by 2a. So we have got this value. That means value of momentum is a factor quantity, so it may be negative also. Okay, that means momentum ranges from minus h by 2a to plus h by 2a. Value of momentum may be any within this range. Okay, within this range. Now you see, classically we have seen that classically kinetic energy may be 0. Okay, and quantum mechanically kinetic energy cannot be zero. Lowest value is this. Okay, now suppose kinetic energy may be zero. Quantum mechanically also say let us assume that mechanically also kinetic energy zero may be zero. Let us assume okay, zero. In that case what will happen? So kinetic energy we have already seen p x square is zero. Okay, that means momentum will be equal to zero. That means if kinetic energy becomes zero, quantum mechanically, if kinetic energy becomes zero, then momentum will become zero. Momentum is zero, that means we know the value accurately. So Px is accurately known. Px is accurately known. Px is accurately known. So uncertainty in momentum will be zero. Accurately known, uncertainty is zero. So uncertainty in position, that will be equal to h by 4 pi by del px, and that will be equal to infinity. So if quantum mechanically kinetic energy is zero, then momentum will be zero. That means momentum is accurately known, and momentum is accurately known means uncertainty in momentum is zero. That means uncertainty in position will be this infinity. But that is not possible. Why? That is not possible. Why? Because particle is here within the region x equal to 0 to x equal to a. Particle is here. So uncertainty in position cannot be infinity. Okay, cannot be infinite. This is impossible. No, this is impossible. Hence, kinetic energy cannot be zero. In quantum mechanics, kinetic energy cannot be zero, because if kinetic energy is zero, uncertainty in position becomes infinity, which is impossible. Okay. Number six is that from particle in one-dimensional box, we can roughly arrive at Heisenberg's uncertainty principle. Okay, particle in one-dimensional boxৰ পৰা আমি Heisenbergৰ uncertainty relation to পাব পাৰোঁ. Okay, we may get the Heisenberg's uncertainty relation. Now, how to get this? So we have already seen momentum ranges from this to this. মানে momentumৰ value এইটো ৰেঞ্জত থাকিব. momentumৰ value ইয়াৰ পৰা ইয়াৰ ভিতৰত থাকিব. ইয়াৰ পৰা ইয়াৰ ভিতৰত যিকোনো value possible. So uncertainty in momentum, that will be equal to say plus h by 2a minus h by 2a, that is equal to h by a. That is uncertainty in momentum. Range, rangeৰ ভিতৰত কিমান ভ্যালু আছে? rangeৰ ভিতৰত এইখিনি ভ্যালু আছে. Similarly, uncertainty in position, So particle to kuntu range ase, the particle is here within this range 0 to a. So any value is possible. So uncertainty in position is a. So uncertainty in position is a. Hence del px del x equal to h by a into a, that is equal to h. Hence del x del px will be greater than equal to h by 4 pi. So we can roughly arrive at Heisenberg's uncertainty relation. So these are the different information which we may obtain from the energy expression. Okay, energy expression. Now let us see what information we may get from the wave function. What information? Significance of psi for particle in one-dimensional box. Say n equal to 1, we have seen energy is E1 h square by 8 ma square, and corresponding wave function is 2 by a whole to the power half, 2 by a whole to the power half sin pi x by a, n equal to 1, n equal to 2, so e2 4 h square by 8 ma square, so psi 2 equal to 2 by a whole to the power half sin 2 pi x by a. Okay, this is the energy level, and this is the wave function, and wave function represents state. Today, this is the energy level, and this is the state. This is the energy level, this is the state, and so on. N equal to 3, we will have energy level. N equal to 3, we have state. Okay, so energy level and state. Now, in order to see the values, see the significance of psi, we have to draw graphs. Okay, in order to look at the value of psi, significance of psi, we have to draw a graph. For that, let me have some points. Like this. Okay, say x and psi 1, psi 2. Okay, psi 1, psi 2. Say x equal to 0. So sin 0, 0. Okay, and psi 2, that is also 0. X equal to a, so a sin pi is 0. X equal to a sin 2 pi is 0. A by 2 sin pi by 2 1. I neglect this portion. Okay, this is a constant term. It may change the value, but it cannot change the nature of the graph. It is a constant. Constantly multiply korle value to change hobo, kintu graph or nature to change no. Okay, so I neglect this term. Okay, then a by 2, this will be 1 sin pi by 2 sin pi by 2 equal to 1. then this will be sine a by 2, okay, sine pi, again this will be 0, again this will be 0, okay. Then say a by 4, a by 4, sine pi by 4, pi by 4, okay, sine pi by 4, that means sine 45, 1 by root 2, 1 by root 2, so 1 by root 2, okay. Now root 2 equal to 1.4, 1 by 1.414 root 2, okay. So 1.414, so 1 by 1.414, that means approximately 0.7, approximately 0.7, okay. Now here pi by 4, pi by 4, pi by 4 means pi by 2, sine pi by 2, sine pi by 2 equal to 1, sine pi by 2 equal to 1, okay. Then say sine 3 pi by 4, 3 pi by 4, so sine 3 pi by 4, that means sine sine 3 pi by 4, x equal to 3a by 4, x equal to 3a by 4. If x equal to 3a by 4, okay, x equal to 3a by 4, 3a by 4, then it will be sine 3 pi by 4, okay, sine 3 pi by 4, that means sine pi minus pi by 4, pi minus pi by 4. So second quadrant positive, that means this is approximately 0.7, once again 0.7, okay. Now here 3a by 4, so 6 pi by 3 pi by 2, okay. This is equal to sine 2 pi and 3 by 4, that is 2, so sine 3 pi by 2, okay, 3 pi by 2, that means sine pi plus pi by 2, that is equal to minus third quadrant sine pi by 2, so this will be equal to minus 1, okay, minus 1. So in this way we can put different values of x, okay. Suppose x equal to pi by 3, just 1 minute, okay. So we can have different values in this way. Now if we draw graph, here x equal to 0, x equal to E, okay, and this is the energy level E1, okay. Now here you see x equal to 0, we plot psi in this way, psi 1, we plot psi 1, x equal to 0, psi 1 equal to 0, x equal to a, psi 1 equal to 0. So these are the 2 points. X equal to a by 2, this is the midpoint, a by 2. Here maximum value, say this is the 1, maximum value, this is the 1. So this is the point here. Now a by 2, this is a by 2, this is the point 1. This is a by 4, a by 4 is somewhere here, and if this is 1, if this is 1.7, maybe this, maybe this. Similarly 3a by 4, maybe this. So if we draw the graph will be like this. The graph will be like this. This is the graph. Okay. Similarly, say E2, energy is E2. Energy is E2. Now if we plot psi 2, then what will be the graph? So x equal to a, psi is 0. Now psi 2, we are plotting. X equal to a, psi is 0. Now a by 2, x equal to a by 2. A by 2, psi is 0. This is the point now. And a by 4, a by 4, a by 4, psi is 1. This is the point. And 3a by 4, 3a by 4. Then now this is minus 1. So the graph will be like this. Freehand drawing. This is freehand drawing. So graph will be like this. Graph will be like this. You see? Graph is this. Here, sign of the wave function is negative. Sign of the wave function is negative. Okay? Sign of the wave function is negative. Here, sign of the wave function is positive. Negative, maybe positive, negative, negative. Okay? We get this type of graph. Similarly, if we plot, say, this is the energy value E3, if we plot psi 3, the graph will be like this. The graph will be like this. Graph will be like this. Okay? So here, this is the point. This is the point where psi is 0. This is called the node. Here, these are the two nodes. These are the two nodes. Node means it is the point where value of the function is 0. Node. Okay, value of the function is 0. Now, it is better to plot psi square. It is better to plot psi square against x rather than psi. Why? Because psi square gives the probability. So if we plot psi square, say psi 1 square. Now here you see it was 0.7. If you square this, it will be 0.49. Square will be less. So now point will be somewhere here. So the graph will be like this. Graph will be like this. Okay. Similarly here also the graph will be like this. This portion it will go like this. My drawing is not good. Okay, it is like this. So this is the node where psi is 0 or probability is 0. Sorry. It is not this. If you square, it will go up. It will square, it will go up. Sorry. And not this. Okay, because we are squaring here negative, if we square it will go up. So not this, not this, go up. So this is the plot of psi 2 square, psi 2 square. Again here do if we plot square, so it will be like this. It will be like this. So these are the two nodes. These are the two nodes. So once again, node means where probability of finding the particle is 0. Well, now here, what is the information we get from this? We get from this graph. What is the information we get from this plot? So you see, when the particle has energy this h square by 8 ms square, lowest energy, that is called the ground state energy. Lowest energy is called the ground state energy. Ground state energy. So when the particle is having the ground state energy, then maximum probability of finding the particle is at a by 2. Maximum probability of finding the particle is at a by 2. Okay, to the edges probability decreases. When the particle is having this much energy, say this is a C and here 4C. When the particle is having this much energy, the maximum probability of finding the particle is at a by 4 and at 3a by 4. Maximum probability of finding the particle is here at these 2 points. At these 2 points. Now at a by 2 midpoint, a by 2 probability of finding the particle is 0. Again here maximum probability is here, here and here. But at these 2 points, probability of finding the particle is 0. Now this is the result which we cannot conceive physically. এনেকুৱা ৰিজাল্ট আমি ফিজিকেলি ভাবিব নোৱাৰোঁ যে এইখিনি এনাৰ্জি হ'লে মিড পইণ্টত প্ৰবিলিটি মেক্সিমাম, এইখিনি এনাৰ্জি হ'লে ইয়াত আৰু ইয়াত প্ৰবিলিটি মেক্সিমাম, মিড পইণ্টত প্ৰবিলিটি 0. These things we do not see physically. We cannot observe physically. So quantum mechanically we are getting some results which we do not observe physically. Okay. So this is all about particle in one-dimensional box. Next time we will solve some problems. We will solve some problems related to particle in one-dimensional box. Okay. Thank you.